Project management. In this lecture, we will go over some introductory concepts in project management. We will learn about the critical path, and we will learn about how to manage the risk or estimate the risk of a project missing its deadline. Project management is a large area of management, and there are you could offer multiple courses on project management. There's also the project management professional certification that one could certainly pursue. Operations management uses project management in many situations. So for example, you want to increase capacity of a factory, you have to do a project to buy new equipment, hire more employees, and on a particular date go live with the additional capacity. Similarly, you want to design a new product, you want to launch a new product. All of these are projects. So for an operations manager, it is important to know the basics of project management. So what is a project? A project is a temporary endeavor undertaken to create something unique. By temporary, we don't mean that it is not important or that the results would go away. A project could be setting up a factory which could exist for decades after it's being set up. So the word temporary does not apply to what the project creates. It applies to the project itself. If you set up a new factory, at some point the project of creating the new factory finishes and the factory starts to operate. So temporary simply means the project has a beginning and an end. If something is endless or repetitive, so you keep doing it in a circle, that would not be a project. Unique means that you do not expect to do the same exact thing with the same exact output repeatedly. Now again, to understand unique, we need to keep in mind that the general domain of the project may continue to other projects. What I mean by that is, if you think about a lawyer, each case a lawyer takes could be considered a project. Now we said that the project must create something unique, but a lawyer takes cases day in, day out. After one case, they do the next case, and they do the next case. So how is it unique? The unique aspect is again in the output. Every case is not going to be exactly similar to the prior cases. Every case a lawyer takes has its own unique circumstances. So the output of the project by the lawyer, which is a legal defense or a prosecution, is going to be different each time the lawyer does this project or a similar project about a legal issue. So for a given project, which would be one construction project or one legal defense or one legal prosecution or one capacity expansion project or one process improvement project, what the project results in, that output is unique. If you are producing many copies of the same part, each time you produce a copy would not be considered a project. So if you start manufacturing an automobile part and you make thousands and thousands of that, perhaps the design and prototyping can be a project, but once you start mass manufacturing, the production of that part is no longer considered a project. Project management is the application of knowledge, skills, and techniques on project activities to ensure the project requirements are met. And the key requirements are usually time, the project has a deadline; cost, the project has a budget; and quality, the project may have certain outcomes that are expected. So if you are making a building, it must meet the construction code for that legal jurisdiction. It must have certain features that whoever is paying for the building may have specified in the contract, like doors and windows of a certain type, heating of a certain type, and so on. All of that, meeting that contract, would be part of quality. Now, we are not going to talk about program management, but if you look at project management literature or you go on to study project management in more detail, project managers are usually, well, maybe not usually, depends on the size of the project, but in many cases, they're not just managing one project. A senior lawyer may be overseeing 10 different legal cases, on each of which the senior lawyer assigns some junior lawyers. So when you're overseeing multiple projects, which are working towards related outcomes, you can say this is a program which consists of 10 projects or 8 projects or however many projects. Right? And that is also an area of study in itself, because some of the projects may share resources and you may have to move resources between them. However, that is not within our purview of study today. Okay, so we talked about projects being temporary, creating a unique output, right? We also talked about projects having a deadline, which is a time limit, and a budget. They have limited resources. Some examples of projects include planning a wedding ceremony or a wedding. New product development, launching a new product. Launching means to advertise it, to have it available on retail shelves for purchase. And a project you all might be familiar with would be implementing a new IT system in an organization like SAP or Oracle ERP system, something like that. Now, project management has several stages. You have to start with defining the project. Then you have to plan how you will do the activities. Then you have to actually execute. You have to do those activities. You have to monitor and control, which means if anything goes off or something surprising happens or some delays happen, you have to manage those. And then closing is where you hand over the deliverables and officially close the project. Okay. We will only be concerned with the first 2 stages in our study today, and most of the time you'll be focusing on the planning required for the project. Okay, so what is the first stage, which is about defining the project? It is really important to define the scope of the project. What exactly will the project do, and what exactly will the deliverables be? Are the deliverables going to be a blueprint, an architectural design of a building, or are the deliverables going to be the actual building? Deliverables matter a lot. Not precisely specifying the scope can lead to what is called scope creep, where you start a project and then people keep asking, or the team members keep saying, we could do this, we could do this. And the scope of the project increases and increases. And scope creep can be very detrimental, because whenever you add to the project, it's going to take more time and more resources. The primary reason of failures of projects to meet deadlines and budgets is scope creep. As a project manager, you must learn to say no after the scope has been determined and agreed upon by the relevant stakeholders. Otherwise, people will get excited as the project starts to take life, and they will want to add more and more features to it. When determining the deadline or the time frame of the project, we need to be specific. It may not be sufficient to say that the project will finish next year. A year is a long time period. When in that year? So often the deadline is specified as an exact date. At this stage of defining the project, it may not be possible to know exactly what resources will be required. So it is fine to express in general terms the resources required. For example, you may not know exactly which people will work on the project, but you might say a project of this size requires 10 engineers. The project manager should be selected at this stage. Some key qualities for a project manager are a good facilitator, communicator, and decision maker. Facilitation is required to acquire resources for the project, as well as to resolve conflicts between project team members or various stakeholders that are affected by the project. Good communication is required to make sure the project scope is known by all stakeholders. Otherwise, you can end up in a situation where a team executes the project perfectly well, but the people who are the customers or the users of the output of the project are not happy because they were expecting something else. And sometimes hard decisions need to be taken, which activities need to be sped up. If somebody should remain a member of the project team, somebody new should be hired, things like that. At this stage, the team may also be selected, or at least some initial work done in that regard. Team members are selected based on their competence, dedication, and their skills to work with each other. It is important to consider when a member joins the project team, whether they will be reporting exclusively to the project manager, meaning are they going to work full-time on this project and just report to the project manager for its duration, or are they going to be working part-time? Are they going to be reporting to their existing boss and doing their existing work as well as working on the project and reporting to the project manager? This is important to know because often conflicts arise when the project manager expects full-time work from an employee who already has other work based on their existing responsibilities. Now let's get to planning the project, which is where we are going to spend a lot of time on. It is a key stage of project management, and a good plan can preempt issues that may arise if one simply starts the project without having a plan. To plan the project, we need to break down the work that needs to be done. A project like construct a high-rise building is going to be a very complicated project. So we need to break it down into smaller activities. Work breakdown structure provides a list of activities. It may group them by stages. So stage 1 is these 20 activities, then we move on to stage 2, which is these 15 activities, and so forth. But we need to know all the detailed steps that need to be done. The more detailed steps we identify at this stage, the better, because then there will be less surprises. Once we identify the activities that constitute the project, we have to identify the relationships between activities. Some activities can only be started once certain other activities are done. For example, we cannot start building the foundation or building the walls of a building before we purchase the land. So the activity of acquire land must precede all the construction related activities. This is called a precedence relationship, and we usually specify it for the construction related activities, we say these activities have a precedent that you must do activity A, which is acquire the land, before you can start these activities. This is an example of a work breakdown structure for relocating St. John's Hospital. You can see level 0 is the entire project, relocate the hospital. Then we break the entire project into big chunks, which are level 1, which is organizing and site preparation and physical facilities and infrastructure. Then each of the larger stages in level 1 are broken down into smaller activities at level 2. How many levels you have is a decision the project manager must take, and it requires experience and knowledge of the context to find the appropriate number of levels. But one way to tell if you have the sufficient levels are if the activities at the lowest level, like level 2, are the most fine-grained activities. If you can read, if you can describe that activity, and you can have some knowledge with consultation with team members about what resources will be required for that activity, how much time it will take. Notice if you just think about level 0, it is very hard for somebody to tell you how long should a relocation of a hospital must take and what it must cost. But if you look at select site and survey, somebody who's in construction and has worked on bigger projects like this might tell you selecting a site and surveying might take 2 months and it might cost this much based on their experience. So you have broken it down to the appropriate level because you have activities where you can know a lot about that activities or find out a lot about that activity based on people's expertise, skills, and experience. When we have the work breakdown structure, we like to represent it as a network diagram because a network diagram visually shows us what the precedence relationships are. In general, network diagrams are used in many, many disciplines, and there are different notations for them. For project management, we are going to use the AON diagram notation, where AON stands for activity on node. In activity on node diagrams, each circle, or you can use squares, the shape doesn't matter, but each node is represented by some shape like a square, a rectangle, or a circle. And the arrows are used to represent precedence. So if you have circle A and then circle B and an arrow going from circle A to B, that means activity B can only be started once activity A is done. So that's the precedence relationship. Let's look at an example. So we're going to continue with the St. John's Hospital relocation example. And we have taken that work breakdown structure and put it in a chart. So we have all the activities A to K listed, and they are, under headings, of, stage 1 organization and stage 2, the physical movement of equipment. At this stage, what we are most interested in is the entire list of activities, activity A to K. The second column of the table lists the precedence relationships. So activity A and B have no predecessors, because if you look at the table, their predecessors are just the start node, and the start node is just a node added so that the network diagram has a starting and a finishing point. It's not really any work. You can just say, okay, let's start the project, and you start the project. Any activities you do, for example, setting up an office for your project or something like that, should be part of the network diagram, right? So unless you're going to do them before you formally start the project. So start just says this is the start of the project. So activity A and B can actually be done in parallel, because when you're selecting administrative staff, somebody who's in construction can go and select the site and do the survey. You can also see in the last column, we have assigned responsibility of activities to different people. And in the second to last column, we have how many weeks each activity is expected to take. This table would actually be the work breakdown structure, WBS, and we can draw a network diagram to represent it. So we take the information in the table and we make this diagram. In practice, when you're making this diagram, always it's relatively straightforward. Just plop down the start node first. So you build this diagram from left to right. So once you plop down the start node, you go to the table and look at which activities have start as a predecessor. That means those activities come right after start. Looking through the table, we see A and B have start as a predecessor. So we follow the start node on our diagram by A and B to the right of the start node, and we draw the arrows. Then we can put the activity times of 12 and 9 on the A and B circles. Then to continue, we'll look at which nodes have a predecessor, which is A, because these nodes will come after A. If you scan the table, you see activity C, F, and I in the table have A as a predecessor. So you can put C, F, and I to the right of A. Similarly, you can find activities where the predecessor is B. You'll find them as D and E. So you can put activities D and E to the right of B, and you connect them with arrows. And you keep going. Then you look at node I, which nodes have I as a predecessor. You look at node F. You keep going until all of the rows in the table, all of the activities in the table have been drawn. Once that has been done, the last activity we put out, which is activity K, okay, we know it is the last activity because no other activity has K as a predecessor. So there's nothing to put to the right of K. That's how you'll know you're done. You plop K in because K has J as a predecessor. So after you draw J, you draw K to the right of J. Once you plopped on K, you know you're done because nothing has K as a predecessor. That means there's nothing to do after K, because if there was something to do after K, that would have K as a predecessor. It would depend on K. So then we can just draw an arrow from K to finish. Okay. So once you have gone through the whole table, drawn a network diagram, you can now visually see the relationships between the various activities. You can identify various paths between start and finish. For example, I can start at the start node. I can go to A, then F, then K, and then to finish. Right? So it's important to be able to identify the paths. You will see why shortly, because one of the paths from start to finish, called the critical path, is really important. So how do we identify paths? You just start at the start node and you just find a path through the maze until you hit finish, and you'll write down all the nodes you visit, and that's a path. And you keep doing that until you've identified all the paths. So what is the critical path? The critical path is the sequence of activities between a project's start and finish that takes the longest time to complete. Once you have completed the critical path, the other activities are, if they're happening in parallel, because they don't depend on the critical path, you would have completed the project, because while you were finishing up the critical path, other project team members have finished up the other activities. Because the critical path takes the longest time, there's enough time for the other paths to finish by the time the critical path ends. So the project completion time is always the time taken by the critical path. Okay. This is assuming we have sufficient resources that the other activities not on the critical path can be done in parallel to the critical path. Because project time, the deadline, is such an important aspect that for now we're going to assume we do have the resources so that two activities which do not have a precedence relationship can be done in parallel. If you are resource constrained and you cannot do two activities in parallel, even though they do not depend on each other, then that is a more complex situation, and we will not be talking about in this introduction on how to handle those issues. You can notice that if you go back to this table, okay, that different people are assigned to different activities. And so when Johnson is doing activity A, Taylor can do activity B in parallel. Johnson does not have to do activity B as well, right? And so that is why, the critical path is going to equal the project completion time. When you're done with the critical path, everybody else is already done. Now, how do we find the critical path? The first method, which is rather simple and many students prefer for small to medium-sized network diagrams, is list all the paths. Add up the activity times to find how long each path takes. The longest path is the critical path. Easy peasy. If the network diagram is kind of big or huge, method one might take a long time, and you may not be 100% sure that you've listed all the paths. What if you missed a path while you were listing all the paths? Then you can use method 2, which is slightly longer, but it's easy and it guarantees that you will find the critical path. You find the slack for all the activities. Then you identify activities with 0 slack. All activities on the 0 slack are on the critical path. Because by definition, if you're on the critical path, your slack is 0. Okay. Now what is slack? So we're going to talk about slack, shortly, but slack is essentially, can you delay an activity without delaying the project? Okay. So if you look at this network diagram, okay, after activity B, D and H are going to take 50 days, 10 plus 40, and then you get to J. And activity E is going to take 24 days. Okay. Now J cannot start until both all H, G, and E are finished. Okay. So if H is still going on and you're done with E, it doesn't really help J because J still has to wait for H. So E here has a slack time because E could start a few days late and still get done before D and H finish. So that is slack because E has a buffer time period. It can actually be delayed without delaying the project because, D and H still have to finish and J still has to finish, right? So E is not the one causing the delay. So E itself can be this buffer around E. You can start a little bit late and still end the project in the same amount of time. So that's the idea of slack. Okay. Now just visually looking and figuring out what the slack is kind of daunting, but this is a simple way to find the slack. And once you identify the slack for every activity, you just pick the activities with slack of 0 and those are your critical path. Okay, now we need to define something called the finish time to be able to find slack. If an activity starts at a particular time and it takes, let's say 10 days, then when will the activity finish? It's a rather simple question. For example, if the duration or activity time for X is 10 days and you start the X activity after 12 days, when will you finish X? Well, 12 is when you start. It takes 10 days, 12 plus 10, 22 days, right? So activity X finishes on the 22nd day. So for any activity, the finish time is going to be the time you start the activity plus the duration of the activity. Now we're going to compute what is the earliest time you can start an activity. It's not 0. You can't start all activities at time 0 because some of them depend on other activities to have completed. Once we identify all the early starts, once we identify early start times and early finish times, we can then identify the late start and late finish times. Early finish time is really easy. If you know the early start of an activity, you add the time it takes to do the activity, and that's early finish. Similarly, late start can be identified going the other way if you know the late finish of an activity. An activity finishes on day 40 and it took 10 days, then it must have started on day 30. Why are we identifying late start in this manner? Why don't we just say late finish equals late start plus activity time t? Well, that's the same thing. Algebraically, you can rewrite this as late finish equals late start plus time t. But you'll soon see why we write that as a subtraction, late finish minus t. If this slide doesn't make sense, do not worry. It's just best to go over an example, and I'm going to do an example now, and you will know exactly what to do once you follow the example. So this slide is just mostly for completion and formality to give you all the definitions and to know what early start means. But once you see the actual process, it's very easy and straightforward. Once we have all the early start and early finish times, the slack is simply the difference between early start and late start, which is also the exact same value you get if you use the early finish and late finish. You could use the start times and the finish times. So let's look at how we're going to do this. We are going to draw some bigger circles so we can write a bunch of numbers in the circle. So in the middle, at the top, is the activity name, or just a symbol for the activity, like A, activity B. Then underneath the symbol, in the middle, the number is the time it takes to do the activity. So it takes 12 units of time to do activity A. We have to keep the units the same, so all activities should be represented in days or weeks or hours, whatever is appropriate. In our example of relocating St. John's Hospital, we're using weeks because the activities involved, take certain weeks to do. They can't be finished in minutes or hours. On the left-hand side, we have at the top the early start time. If A has no predecessor, then you can start A right away, which means A can start at time 0. Time 0 means the project starts. Project starting is time 0. You turn on the stopwatch as the project starts. So we can start activity A at time 0. Why? Because it has no predecessor. Nothing needs to be done before you do A. If you start activity A at time 0, which is the early start time, what would be the early finish time? Well, activity A takes 12 units of time. So 0 plus 12 gives us the 12 on the top right, which is the early finish time. Okay. Now, how do we get the late finish and late start? We will see that as when we go through the network, but imagine you knew the late finish was 14, right? That we had to finish A by the 14th day. Why? Because the B activity or C or whatever activity depends on A must start by day 14. So we have to finish A by 14. So let's say we knew that. Then what would be the longest we could delay starting activity A? Well, if A must finish by week 14, sorry, these are weeks, week 14, and it takes 12 weeks to do, then 14 minus 12 gives me 2. So activity A must start, after the second week. Otherwise, you'll not be able to finish it by week 14. So 14 is like a hard deadline for A. That's the latest finish. Do not finish beyond this. You must finish by late finish time. That's a deadline, a hard deadline. So the hard deadline to start is 2 after week 2, because otherwise we'll not meet the hard deadline to finish. Okay, so let's identify the critical path using both of the methods. Okay, method 1 is we list all the paths. So I could find 5 paths through the network: AIK, AFK, ACGJK, BDHJK, BEJK. Okay, and these are all the paths that are possible through this network diagram for St. John's Hospital project. Then I can add up the times, right? If I go back to my table, I know how much time each activity takes. So if I have path AIK, that's going to be 12 plus 15, 27 plus 6, 33 weeks. So the path AIK takes 33 weeks. So let's go back to our example, right, where we're listing all the paths. Right? So AIK takes 33 weeks. You do the same thing for the other paths, add up all the times, and we find that the longest path in terms of time duration is path BDHJK, takes 69 weeks. No other path takes 69 weeks. So the critical path will be BDHJK. Okay, and there's only one critical path, as only one critical path takes this maximum amount of time. If there was another path which also took 69 weeks, then both paths would be considered critical paths. You would have 2 critical paths. Now let's do it with method 2, finding the early start, early finish, late start, late finish of all activities, so that then we can find the slack and when we can identify the critical path using slack. This is the same network diagram for St. John's Hospital example. I have simply listed in the middle each activity label A, B, C, and the duration, the activity time, how long it takes to finish that activity. So first I'm going to do what is called the forward pass. The forward pass means you start at you start at the start node and you work your way to the right side until you reach the finish node. Okay, so starting at the start node, I see that I can go to A and B. What is the earliest I can start A and B? Well, A and B don't have any predecessor activity because start is not really a real activity. It's just like a signal that you've started, right? It's just a point marking the start. It's not a real activity. So A and B can start right away at time 0. So the earliest start time for A is 0. It has no predecessor. What is the earliest finish time for A? Well, A takes 12 units of time, so 0 plus 12 gives me the 12. I can do the same for B. B can start at time 0. It has no predecessor. It takes 9 units of time to finish, so 0 plus 9 gives me the 9. Now, once you have A and B, you can do the nodes which come after A and B. So D comes after B. If B finishes at 9, D can start at 9. Well, why? Well, because D only depends on B, and B is done at time 9, at the end of 9th time period, right? 9 weeks. So if B is finished in 9 weeks, then D can start right after 9 weeks. Okay. If there was another predecessor, it'll be more complicated. You'd have to look at both of them, right, and pick the maximum. Same thing for E. It only depends on B. So B is done at 9, so we start at 9 right away. Then we can do H, which comes after D. Now J is going to be the complicated case because J depends on 3 activities, G, H, and E. Now if I look at H and E, they are, E will be done at time 33, H will be done at time 59. So can I start J at time 33 because E is finished at 33? Nope, H is not done. Can I start J at time 59? Well, I have to know when G finishes. What if G finishes at time 60? Then I can't still start J at 59. So you have to look at all of the predecessors, all the arrows coming into a node. You have to look at all of them when you can start that node. So I can't do J until I do G. So I have to go back to A and I have to start filling up, the C and the F and the I. So I can fill out the C because A ends at 12. So C can start at 12. And then C takes 10. So 12 plus 10 gives me the 22. G only depends on C, so G can start at 22, and then G takes 35 units of time, so 22 plus 35 gives me 57. Now I can do J because 57, 59, and 33, the 3 activities leading to J, well, the maximum time is 59, so at time 59, all 3 must be done, so J can start at 59. Okay. Now I cannot do K from J. K cannot start at 63 because you have also to look at I and F first. So we can do I and F based on A. They start at 12 and they finish at their respective times. And now I can do K. I finishes at time 27, F at 22, J at 63. When can I start K? I recommend you pause the video and figure out when K can start and then unpause to see the answer. If you said 63, you would be right because you cannot start at 27. J is still not done. You cannot start at 22. I and J are still not done. But at time 63, all 3 would be done. So we can start K, and K takes 6 time units. So 63 plus 6 is 69. Okay. So right now, when I've completed my forward pass, I've gone from start to finish, putting in the top values, early start, early finish for all activities. I know that my project is going to take 69 weeks. We saw from method 1 when we listed all the paths that the critical path is 69 weeks, and we see the same thing. The earliest time the project can finish or be completed is 69 weeks. Now to get the late finish and late start times, I have to go back from finish to start in the opposite direction, which is sometimes called the backward pass. You go from right to left, from finish to start. So to start off, you simply copy the 69 down to the late finish time because 69 is the time the project takes. So all activities must finish by time 69. So the late finish has to be 69. So for K, I just copied the 69 down for the late finish time, which is the bottom right time. Now I subtract the time it took to do K, so K must have started by time 63. Okay. Now I can go back and move the 63 to activity I, F, and J. They all must have a late finish by time 63. They must finish by 63 because K needs to start, has a late start of 63. So this 63 gets propagated to the three predecessors of K. For each of the three predecessors of K, you subtract from the late finish time of 63 in blue on the bottom right, the activity time. So for activity I, you do 63 minus 15 to get the 48, the late start time. Notice for activity I, you can start it at time 12 and finish at 27. That's the earliest, that's the best you can do. But worst case, you can start activity I at time 48 and finish by 63 and still finish the entire project by time 69. So late finish, the late start and late finish are those times that if you use these late start and finish times, you can still finish the project in the same duration it took with the early start and finish times. You can see for activity J, the late start and late finish are exactly equal to early start and early finish. That means activity J is on the critical path. It must not be delayed. It has a slack of 0. If it were to be delayed, the whole project would get delayed. However, activities I and F have a lot of slack. They're not on the critical path. They could be substantially delayed without affecting the completion time of the entire project. So what is the slack for activity I? Well, you could do 48 minus 12, that'll give you 36. Okay. Or you could do 63 minus 27, it'll give you 36 as well. So the two numbers on the right, late finish and early finish, the difference between them is the slack. Also, the difference between early start and late start on the left, that's also slack, and the two numbers will always be equal. If you get a different slack using the finish times than using the start times, then you have done a calculation mistake. Once we propagate the 63 back to activities I, F, and J and find the late start times for them, then we can work back from I, F, and J. The 59, which is the late start for J, can now propagate back to E, H, and G and become the late finish for these three activities. Then as usual, we subtract from late finish the activity time to get the late start time, which is on the bottom left. So we continue this backward propagation till we get back to the start node. Okay. So now I have filled in these 4 numbers for every single activity. On the top left, I have the early start. On the top, looking at the screen, so if you're looking at this computer screen, then on your top left is the early start. On the top right, early finish. Bottom left, late start. Bottom right, late finish. Okay, so the arrows mark what those numbers are. Now we can find the slack. Slack is simply the difference between two numbers on the right side or the left side of an activity. So either you look at, for activity A, you could look at 12 and 14, which are the early finish and late finish times, and the difference between them is 2, so the slack is 2. Or alternatively, you can look at early start and early late start, which are the two numbers on the left of A, which is 0 and 2, and the difference between them is also 2. So the slack is going to be 2, whichever side you look at. So you go through and you write the slack for all the activities. So the slack for activity I is kind of, on top of this title. So it is 26, right? And you can see that some activities have a slack of 0. 69 minus 69 for K is 0. 63 minus 63 for J is 0. 59 minus 59 for H is 0. All the activities which have a slack of 0, the ones in red, are the critical path, which is, B, D, H, J, K. That's the critical path. And that's what we found using method 1 as well, when we listed all the possible paths. Notice using the slack method does not require us to list out all the possible paths. You just do the activity times, early start, early finish, late start, late finish. You find the slack for each activity. and you simply select the activities with a slack of 0, and those those form the critical path. Now, if you use software and you have a tool for making a Gantt chart, you can have activities depend on other activities using precedence relationships. See the predecessors column here. And then the Gantt chart would draw these arrows to show which activity depends on which activity, when is the earliest you can start an activity, and when is the earliest you can finish. So it will give you the early start and early finish times in this sort of visual representation. Microsoft Project, is able to do a Gantt chart like this. So there is software you can use to identify the early start and early finish. Notice the red on the right. See, you have a lot of activities in blue, but you also have some red, and the red is the critical path. Depending on the software, it may not be, but you can check your software's documentation to see what is the critical path. For this course, you just need to do it by hand. We are not using any software. So you are expected to do this by hand, find the early start, early finish, and the critical path. Now, once we have made this, activity on node diagram, we have found the critical path. What are the advantages, right? The first advantage is you know which activities to focus on to make sure they finish on time. Which are those activities? The ones on the critical path. Every minute a critical path activity is delayed, the whole project is delayed. Okay. For activities not on the critical path, you know their slack value. So you know those activities can be delayed by the slack without affecting the project completion time. So that's a huge advantage in planning, because then you can plan your resources to ensure that the critical path activities are done on time. Now, sometimes when you're estimating activity durations, this activity will take 10 weeks, this will take 5 weeks. You could be wrong. You may not know exactly how long it will take. So there's risk. You might say, well, the project will finish in 69 weeks. And if your project deadline is 72 weeks, you might feel really happy. Well, my critical path is 69 weeks. Deadline is 72 weeks. So yeah, I'm home. I'm good. But if the activities take a different amount of time than you were expecting, the total amount of time the project takes can change. So to manage this risk and delays of the project, we can try to estimate this risk or quantify this risk using a technique called PERT, P-E-R-T, Project Evaluation Review Technique. Okay, I don't know how evaluation is different than review and why it's called PERT, but that's just the name project management people decided to use for it. Okay. So let's talk about PERT to see how it can help us figure out what is the risk that we are taking, whether we'll be able to finish this project on time or not. And if the risk of not finishing on time is too high, we could look to reduce activity times. How can you reduce an activity time? You maybe give it more resources, right? Or you may be able to break it up into multiple activities and do them in parallel. So there are multiple things you can do to change your work breakdown structure, either add more resources or break down activities differently to affect the activity times, how long each activity takes. Now, PERT likes to use what's called a beta distribution, okay, which is drawn on the screen for you. And that distribution is kind of like the normal distribution you're all used to. With the exception, it is kind of like a hump, but the exception is that on the right-hand side, you have some skew, so you have a longer tail. Now, depending on the values of A, M, and B, the skew could be on the other side, so the hump could move depending on what are the values of A, M, and B. So what are A, M, and B? The normal distribution, if you recall the normal distribution, which is on the right, to specify the normal distribution, you need to know the mean and the standard deviation, just 2 parameters. But for the beta distribution, you need to know 3 parameters called A, M, and B. Actually, you need to know alpha and beta, which depend on A, M, and B. So we'll talk about that on the next slide. But it's easier to think about it in terms of A, M, and B. A is the optimistic time. If everything goes perfectly, what's the best case time to finish an activity? So you might say, well, activity A, can be done in 7 weeks if everything is on time and we work really hard and everything happens exactly according to clockwork. B is the pessimistic time, which is the worst case scenario. Okay, if everything kind of goes wrong, how long is it going to take to do activity? That's the lowercase b. The M is not the mean. So if you look at this picture, you'll notice the mean in the black line here is somewhere closer to B, but in this diagram, the M is closer to A because you have a right skew. And the M is what's called the mode. The mode is the highest point on the probability curve. So you can see it corresponds to the peak, which is that's the most likely thing that's supposed to happen. So the highest probability is that the amount of time taken will be M. So that's the most likely time. If M is closer to A, then you're going to have a skew to the right where most of the time you are around M and close to A, but sometimes you can be really far off and towards B. If M is a value which is closer to B than to A, then you're going to have a left skew where most of the time you take a long time closer to B, which is the M there, and around M, and then sometimes you take a very short amount of time. So depending on what M is picked, you could have a distribution which is not symmetric around the mode, right? But if M is halfway between A and B, then you may get a very normal looking distribution, which is kind of very close to being bell-shaped. Now, if you do use statistical software, actually I talk about that afterwards. So let's first look at, well, what is the average value? So notice if you look at this picture, you can see the mean, which is between M and B in this case. It could be between A and M as well. Like I mentioned, it depends on the location of M with respect to A and B. But the mean is not M. So what is the mean? And what is the standard deviation of this distribution? Well, we can find those numbers by these formulas. A, which is the optimistic time, the smaller number, plus 4 times M plus B divided by 6 is the average or the mean of the beta distribution. And the variance of the beta distribution is going to be A minus B divided by 6 and the whole thing squared. Okay, so some software like Excel, well, if you want to use a beta distribution to do some calculations or a simulation, they will ask you 2 parameters, alpha and beta, for the beta distribution. Alpha and beta depend on the A, the B, and the M, the optimistic, A, the pessimistic B, and the most likely M values. And these are the formulas. So if you want to go ahead and use a software like Excel or other software for the beta distribution, and you have the A, B, and M values that we discuss here, you can convert them into alpha and beta values and use that software. Okay. So notice the average value is not alpha and the variance is not beta. They're different parameters. So, so the average, is computed as A plus 4M plus B over 6, and the variance is computed as A minus B over 6 squared. And the average and the variance is what we want to know, because we're going to work with the average and variance values of the various activities. So we're not going to work with alpha and beta that are given here, but if you were to use Excel or some other software to do simulation about your project's risk and so forth, then you would convert the A, B, and M into alpha and beta for that. So these are the activities that are A to K for the St. John's Hospital project we've been talking about throughout this lecture. And we have the activity expected times, the T of E, in the second last column. These are the times we've been using so far. We said A would take 12 days, B would take 9 days, and so forth. But these are the expected times. A might take as little as 11 days and as much as 13 days. So the first three columns give us the optimistic, the most likely, and the pessimistic times for each activity. Now, if you do B, which is this column here, pessimistic time B, minus A, which gives you 2, you divide the 2 by 6, you get 1/3. You square it, you get 1/9. 1/9 is about 0.11, which is the variance of activity A's duration, or the time it takes. So we can take the A, M, and B values and find the expected time, TE, and the variance, and fill out the last two columns. Usually you're given just these first three columns, the A values, the M values, and the B values, and you have to use the formulas here, these formulas right here. T sub E will give you the average time for each activity, and the sigma squared, the variance formula, would give you the variance for each of the activities. So using those formulas on slide 24, we compute the second last column of expected activity times and the last column of the variance in activity times. Okay. Now, how do these activity times, which now have a mean and a variance, relate to the project completion time? Well, project completion time is simply the sum of the time it takes to do the critical path, right? So we will say capital T sub P, the time for the whole project, will just be the sum of the expected activity times on the critical path. What are the expected activity times? If you go back to slide 26, those are the times in the second last column, T sub E. So A, M, and B are not the expected times. The most likely time, M, is not the expected time. So students sometimes make the mistake, they add up the M values and they said on the critical path, and they say that's how long the critical path is most likely going to take. So that's the project completion time. Most likely is the mode, and in a beta distribution, the mode may not equal the mean or the average value, and you need to add up the average values to get the average project completion time. So you have to find the expected time, the average time for each activity first, and you have to add up these expected times for the activities on the critical path to get the expected time for the whole project. So capital T sub P is the expected time it would take to finish the whole project, which is simply the sum of the activity times on the critical path. And because these activities are now random, they're variable, they take different amounts of time, the total project can take different amounts of time. It's not always going to take 69 weeks, because some activities may take less or more than we think they might, right? So the variance captures how much the total time can move around, and that's simply the sum of the variances of activities on the critical path. So let's actually do that, right? For the St. John's Hospital example, critical path is BDHJK. So I add up the expected time, the small t sub E column from my table for B, D, H, G, and K. So B has an expected completion time of 9 weeks, D has 10 weeks, and so forth. So I add all of these up. So my expected completion time for the whole project is 69 weeks. Okay. Now I add up the variances of the same activities. Variance of activity B is 1.78. So if you go back here, you can see that the variance of activity B is 1.78. And same for activity D, the variance is 1.78. So you go through that table and you simply add the variances only for the activities on the critical path, not all of them, just the ones on the critical path. And you get the variance for the project completion time of 11.89. Now we know that the total project completion time has an average of 69 and a variance of 11.89. We can answer probabilistic questions about how long the project will actually take. So if somebody says our deadline is 72 weeks, what is the probability that we will actually meet the deadline and finish within 72 weeks, or take up to 72 weeks? Taking up to 72 weeks, less than equal to 72 weeks, well, we can look at this mean and variance, and convert the threshold of 72 into a z-score and then use the normal probability distribution to find the probability. Okay. So we'll do 72, our threshold, minus the expected times 69. That gives us 3. Divided by the standard deviation, which is simply the square root of the variance. So if the variance is 11.89, the square root of that will be the standard deviation, divided by 3.45, the standard deviation. Then 3 over 3.45 gives us 0.87, which is the z-score corresponding to how far 72 is from 69 on the standard deviation scale. If you're rusty on z-scores, just follow this procedure. But you should recall that from when you studied the normal distribution. Okay, so this is illustrated on the picture here. The area in the blue is when you are below 72 weeks, right? And the 69 is the average value of the normal distribution. So you might say, oh, wait a minute. We have been talking about the beta distribution. We use the beta distribution to compute the average activity times. We use the beta distribution to compute the variances of the activity times. How did we suddenly get to a normal distribution? We're going to rely on the statisticians and probability modeler's best friend, which is the central limit theorem, which says when you add a bunch of stuff up, which could have any distribution in the world, the sum of adding a bunch of different stuff up is going to be the normal distribution. Yeah, it's going to approximate the normal closely. So we are adding, activity times of 5, 6, 7, 8, 10, whatever many activities up to find the project completion time. So that even though the individual activities have a beta distribution, the total project time will tend to have a very normal distribution, which makes our job easier. We can calculate this probability using the normal distribution, which we are familiar with. So we draw for the total project time only, we use the normal distribution. And the total project time has an average of 69, has a variance of 11 point something, which is a square root of that is standard deviation of 3.45. And when we compare to 72, we find the area to the left of 72 under the curve, and that's the probability that we will finish the project on time. So we can find the area under this curve, the blue area, using the norm.s.dist function, where we pass it the z-score of 0.87, which we computed right here. So the z-score of 0.87, we pass it to this Excel function, and we get a probability of 0.81. Now I am rounding this z-score to 2 decimal places, but you should not. You should do this calculation in Excel and keep like 4 or 5 decimal places, and then use this formula in Excel on the exact value. So do not round to the intermediate work to 2 decimal places. Okay, so the final answer, the question might ask you, give me the probability to 2 decimal places. So remember, probability is always less than 1. So you should be getting an answer less than or equal to 1, which is true. We get 0.81. So there's an 81% chance, or a probability of 0.81, that the project will finish on time within the stated goal of less than or equal to 72 weeks. Now we could ask the same question about other paths which are not the critical path, but which are close to being the critical path. So we have a path ACGJK, which has a length of 67 weeks. Remember, the critical path had a length of 69 weeks, so this is almost a critical path, right? So maybe because the activity times, the actual activity times may be different than what we expect because they have a beta distribution, they move around their most likely value. Sometimes they're less, sometimes they're more than the most likely value. So maybe it could end up that this path takes more than 69 weeks and ends up delaying the project, even though it's not strictly the critical path based on expected durations. What is the probability that this path will also finish within 72 weeks? Well, we can do this, repeat the same exercise. We know that the sum of the activity times of ACGJK is 67. We add up the variances from the table we had to get the total variance of 15.55. Again, we convert to z-score. 72 is our threshold value, the project deadline, minus the expected time of completion of the path, 67, divided by standard deviation of the project completion time, of 67 weeks, which is 50.55, the variance. We take a square root of that, we get 3.94. That gives us a z-score of 1.27. Again, we're going to use the norm.s.dist function, pass it 1.27 comma true, we get a probability of 0.90. So the probability is there's a 90% chance, or a probability of 0.9 that this path will finish within 72 weeks. So there's a good chance we're going to finish within the deadline, because our critical path had a probability of 0.81 and our second longest path had a probability of 0.9. So there's a strong chance we're going to finish within 72 weeks. Now you can, if you don't want to do the z-score step, you can also actually use a norm.dist function. Okay, you would pass it the value 72, comma, then you would pass it the mean value 67, comma, then you would pass it the standard deviation of 3.94, which is the square root of 15.55, comma, true, and you can use equals norm.dist in Excel as well. Okay. I just find norm.s.dist is easy as well. Just, calculate the z-score in one cell, and then in another cell in Excel, you just plug in this formula and you refer to the value in the first cell, and it gives you the probability. Okay, so that is all for project management. I just want to recap briefly. Okay, so in this lecture, we talked about some initial ideas about, defining the scope of the project, making a work breakdown structure, right? Then we talked about how to represent a work breakdown structure in a table into a network diagram. Then we talked about how to find the critical path. Okay, just finding the critical path is sometimes called CPM, where CP starts for critical path model, or something like that, right? So in project management notation, you'll hear about CPM and PERT. CPM just means you have fixed activity times. The activities take, a fixed time given in this table all the time. There's no randomness or variation, which is unrealistic, but CPM makes that unrealistic assumption, and then you just find the critical path, right? And then you say, okay, that's how long the project will take, period. Then we talked about, risk analysis using PERT. We said, well, activities don't just have one time that they will take for sure. Each activity may have a most likely time, an optimistic time, a pessimistic time, M, A, and B. M is the most likely, A is the optimistic, B is the pessimistic, right? And then we can convert these A, B, and M values to an expected or average time for each activity and a variance for each activity. And then, we can use, make this table. The average times we compute in the second last column, and then the variances we compute ourselves. The first three columns should be given to us, A, M, and B. The last two columns we compute using the formulas right here. Okay. And once we compute them, then we can look at, we can compute the expected project completion time, capital T of P, and then the variance in that. And then we can compute probabilities, how likely it is that we will finish within the deadline. Now, what do you do if you cannot finish within the deadline? Well, you can revise the deadline if it's the start of the project, or you can add more resources to activities. Sometimes that's called crashing. Crashing means, the activities on the critical path, you add more resources to them to do them faster. So your critical path becomes shorter, and hence your project duration becomes shorter. Right. So we're not going to talk about crashing in this lecture, in this video, right? But that is something that can be done if the expected project duration is too long, and it is beyond what the stakeholders will accept. Okay.